So we are now doing chapter 1, and my idea of how this is going to go is for you guys to go ahead and just read through the vocabulary on your own, and then afterwards you can watch the video and we'll go over the example together, and then pause to continue the vocabulary and so on, and we'll see how that goes. And you can see I have a calculator here on the screen, so we can also go through all of our calculator steps together. So here's the first example in the notes. Suppose we are studying the eye color of Fullerton College students. We choose 200 random students and record their eye color. A. What is the population? So the population is the entire group to be studied. So in this case, the population would just be Fullerton College students. B. What is the sample? The sample is a subset of the population that is intended to represent the population, and in this example, that would be the 200 random students. And then this should say part C. What is the data we are collecting? And that would be their eye color. So now you can go ahead and continue reading the vocabulary, pause the video for a moment, and then you can go ahead with me on the next example. Suppose we found out that of the 200 students we chose, 76% of them had brown eyes. Did we find a statistic or a parameter? Well, because this data was collected from a sample, anything you compute from that data would be considered a statistic, because statistics come specifically from samples, whereas parameters come from populations. Part B, is this descriptive or inferential statistics? Because it's simply just giving a number, I mean, in this case, just listing out the data or the 76% compiled from the sample, that would just be descriptive statistics. And then part C says, how can we make this inferential? Well, to make statistics inferential, you would need to generalize them or extend them to the population. So you could say something like 76% of Fullerton College students have brown eyes. Now we don't know that. We found that 76% from a sample. However, we often can't get data for a population because populations are quite large. And usually a sample is the best we can do, but we usually report them by generalizing that data to a population. Next example, Gallup did a survey of 1,006 American adults asking what worries them most about your personal financial situation in the long term. Of the people surveyed, 18% said they were most worried about having enough money for retirement. Gallup reported that 18% of all American adults were most worried about not having enough money for retirement, with a 4% margin of error with 95% confidence. That last part, that margin of error stuff, that we will get to and discuss more in Chapter 9. So part A, what is the research objective? So what did they want to find out? Well, it was to find out what worries Americans most. What worries Americans most about long-term financial situation. Okay, part B, what is the population? In this case, we can see that is American adults. However, there are tens of millions of American adults, so they had to select a sample. What is the sample? 1,006 American adults. D, list the descriptive stats. So what they gave us was this 18%. 18% were most worried about retirement. E, what is inferred? Well, you can see in the beginning of the last sentence it says Gallup reported that 18% of all American adults were most worried about not having enough money for retirement. So they made an inference there. They took their 18%, which they obtained from a sample, and they generalized it to make a statement about the population. Let's go ahead and just copy down what they said. 18% of all American adults were most worried about not having enough money for retirement. Next, we're looking at categorizing different types of variables. So it says categorical or quantitative. Height in inches. Height is a numerical measure, so that would be a quantitative variable. Quantitative. B, number on a baseball jersey. So even though it's a number, it is not a measure. Okay, so because of that, it would not qualify as being a quantitative variable. You can't do meaningful arithmetic on baseball jersey numbers. So that one would be categorical, even though it's a number. Not every single numerical variable would be quantitative. Part C, gender, would of course, that's a way to categorize people, would be categorical. So we're going to furthermore classify quantitative variables as discrete or continuous. So part A, the number of kittens in a litter. That is something that you would count, so we would consider that to be a discrete random variable. Part B, the length of a cat's tail in centimeters. That is something that you would measure, and decimal values would make sense, so we would call that a continuous random variable. On this example, we're being asked to decide if what's given is an observational study or a designed experiment. Part A, a survey is conducted asking 400 people if they prefer Coke or Pepsi. If it's a survey, that's something that's very passive. We would consider that to be an observational study. Part B, 200 people are asked to perform a taste test in which they drink from 2 randomly placed unmarked cups and are asked which drink they prefer. So this is considered an experiment because there's an action taking place. It is more active than passive. People are actually drinking the drinks this time. So we would call this one a designed experiment. A nutritionist puts 20 random adults on a strict, low-calorie diet and a rigorous exercise regimen. After 4 weeks, they have lost an average of 4.6 pounds. Is there potential for confounding? Well, you can see that she put all 20 of them on both the diet and exercise program, so because she did not separate these explanatory variables, there is going to be a difficult time deciding which one or both or what combination of them resulted in the success. So the answer is yes. She, is it a she? It doesn't say. She did not separate the explanatory variables. So a better way to do this would be to put some of them on a diet, some of them on an exercise plan, some of them on both, and maybe some of them on none. Part B, what are some lurking variables? Okay, so we're talking about weight loss, so some things could be lifestyle, age, genetics. There are plenty of lurking variables that were not considered in this study. Next example, are young couples who marry or cohabitate more likely to gain weight than those who stay single? Researchers followed 8,000 men and women for 7 years. At the start of the study, None of the participants were married or living with a romantic partner. The researchers found that women who married or cohabitated during the study gained 9 pounds more than single women, and married or cohabitating men gained on average 6 pounds more than single men. What type of observational study is this? Well, a group of people with some similarity were followed over a very long period of time. That is called a cohort study. B, what are the explanatory and response variables? So it looks like what they're trying to use to explain something would be the marriage or cohabitation status. And then the response variable would be a weight gain. Okay, part C. Identify some potential lurking variables in the study. So once again, we're talking about weight gain, so there could be things like lifestyle, age, whether or not they have children might matter, genetics, maybe even something like socioeconomic status. There's a lot of things here that could have an influence that were not part of the study. And then D, can we conclude that cohabitating causes weight gain? And the answer is absolutely no. You can never use a study to claim causation. You can only use a study to claim association or correlation. If you want to claim causation, you must do an experiment, but experiment here wouldn't really be practical, so a study was probably the best they could do in this scenario. In this example here, we're going to use a random number generator to obtain random integers from our calculator. So it says in the example, use a random number generator to select 5 random students from this class roster. So we see that the roster has 25 names on it, and we want to select 5 of them randomly. Human beings are pretty much unable to pick numbers randomly without some sort of bias. So it's usually best to, draw the names out of a hat or in this case, use a calculator. So on your calculator, you're going to go to Math menu, arrow across the top of the calculator to this probability menu, so the right arrow here. And then we're going to use number 5. It says randint. That stands for random integer. So go ahead and press enter, or you can press the number 5 itself. And it's asking us for a few things. Lower and upper refers to the lowest and highest numbers you wanted to choose from. So the lowest number on our list is 1. The highest is 25. And then n is the sample size that you want. In this example, it asks us to find 5 students. Now we'll go down to paste and we'll press enter. Okay, now we want it to run the random integer operation. Press enter again. Okay, so it picked 5 different numbers. The calculator does sampling with replacement, so sometimes it will give you repeated numbers. If that's the case, you can just do this again. You can ask it for 1 more or 2 more or however many more random numbers that you need. So what my calculator selected is most likely different from yours. That's totally fine and expected. So mine picked Xavier, Walter, David, Miguel, and Kevin. And of course, you may have selected 5 completely different people, just depending on the random numbers your calculator gave you.